All right, so welcome to day two. I will try my best to help you understand everything now. So let me help you out with a little review of what we did day one. I know it was a little bit challenging here. Let me try to draw things again. So let's just make this the gravitational side again and the electric side. Let's go over the forces. The electric force is equal to Q times the electric field. So what does Q mean again? That's right, the charge. Here, F equals mg. Okay, so force, then here we have mass, here we have charge, and then here we have the different fields, okay? Let me rearrange these equations for you real quick. Let me rearrange them to help you understand what a field means, okay? So let's just think of a field, okay? Think of a field of plants. Are all of them the same height? Possibly if they're trimmed very well, but for the most part, no. Right? Plants grow in different heights, and so let's kind of use that as an example. Imagine I grabbed a rock and just held it 1 meter above the ground. You can all understand. You can all tell me what's the acceleration due to gravity would be of that rock. But what if I grab that same rock and put it between the Earth and the Moon? Would that still be g? No, that would definitely be different, right? So, what we can think of a field is the value of the force acting on this particular mass in this specific location. So what this means is that G will change depending on the location of space that it's in. So technically, it is related to the center of the Earth. So even if I have this here or this here, there is a very small change on what the value of G is. Same thing with charges. Okay, so again, so this gravitational field, this that it normally as the acceleration due to gravity, it's in general terms, it's a field. And it is the strength of how mass is connected to that force in the gravitational sense. So again, this is the gravitational field when it's excuse me. So mass is connected to the gravitational field, same as the electric field is connected to the force, but with charge. So these are both fields of their own, relating to the force with respect to what they're sensitive to. So mass is sensitive to the gravitational field, and charge is sensitive to the electric field. Hopefully that clarifies things again. So let me show you again, just a quick rundown of what we've seen before. The potential energy, I'll just call it PE due to gravity, and PE in the electric side. So again, we usually have some mountain, right? Some cliff, and we have some object right here. Okay, if I let go of that object, where is it going to want to go? Is it going to want to go up at all? No, of course not. You all know it's going to want to go down. And this is the direction of that field where it wants something with mass to go. So this field wants to move this mass in that direction. Hopefully you can see that. So this represents the gravitational field, okay? And this represents the mass, some object. And of course, the potential energy due to gravity is just the force right here, times some distance, okay? We call it height, but really, it's just the distance between here and here. So it's potential energy because it's this force times the distance, which is work, right? So energy and work are definitely related. So it's how much this force can act upon for that distance. And this is actually quite similar too, just on the electric side. So we have this same force right here times some distance. That is the electric potential. However, before I get into the potential energy again, let us go over the electric field. So this is 7th grade stuff. So if I have a proton, is the electric field going to want to go into it or go out of it? Is it going to want to end there or start there? If you remember well, it will actually want to begin and move away from here. The opposite is true for a negative charge. For a negative charge, it will want to end there, so it wants to pull things towards it. Okay, and because this was kind of discovered a very long time ago, our initial idea is that most charges that moved were positive. So that's why we say if we have a positive charge here, what's it going to want to do? Move away. If I have a positive charge here, what's it going to want to do? It is going to want to go towards here. So that's why the fields go in those directions. So on the gravitational side, there's only one direction here. On the electric side, there are two different directions, either away from here or towards here. However, if I create, okay, so if I have two metal plates that I can change the charge of, if I can make one positive here, and I can make one other metal plate that are parallel, so these two are parallel, this positive and this negative, then I can create a uniform field going from where to where. Okay, hopefully you should see that it'll go from the positive to the negative. So this is the direction of the field, similar to this. Okay, so if I have two different plates, I can have only one direction of the field. Okay, so that is the difference between these fields. So gravitational field going down and the electric field going from positive to negative. So originating and then ending here. So this is, so they both, if I have an object with mass, this can experience a force. If I have an object with charge, this can experience a force. So if I have a positive charge here, and I just drop it like I would a rock off a cliff, where would this go? This would want to go this way or this way? Yeah, positive wants to go to negative. So this is the part that gets tricky. If I have a negative charge here, where's it going to want to go? It's going to want to go in the opposite direction. So depending on the charge, the electric field can behave or can make a charge behave differently. So that is, I guess, what is a little bit tricky about this idea. Okay, so however, when we think positive and we think negative, we think of high potential and low potential. Think of this right here. Okay, what happens if I grab this rock right here and I moved it even higher? Okay, what if I increase the positivity here? The same thing, it would increase the potential energy. So remember, these energies are the force times some distance, right? And then this distance right here would just be the from here to here. That would be that distance. And this one would experience this distance. Do you see that? From here to here. That is the potential energy that it experiences. So if you let it go, it'll move, and then the potential energy would change, right? It would convert into kinetic energy. Same thing here. Now, this is where I want you to kind of rethink what you already know. So this is force times distance. Now, let us think of it as, instead of force times distance, right? Force times distance. Let's think of the gravitational field times that distance. Gravitational, or the field times that distance, the electric field times this distance, times what it's sensitive to. Here the mass, and here the charge. So this is what we call electric potential. okay, it's as if I don't actually care about the value of this charge. I don't care about the value of the mass of this rock. I could have any mass. I could have, 1 kilogram, 100 kilograms. It's going to want to do the same thing, right? So if I have a 1 kilogram rock or a 100 kilogram rock, are they going to hit the ground at different times? No, we should know that they're going to hit the ground at the same time. Okay, same thing here. That's what's going to happen. So this is dependent not on the mass, not on the charge, but on the field and the distance that it can move. So from here to here, from here to here. Now, this is what we call V, which is electric potential, which is measured in volts. So, remember, so V equals E times D, and this could be the gravitational potential. However, we don't normally look at it that way. We just think of height. Hopefully that helps you out. Actually, I didn't want to end it that way. One thing I did want to end it on is let's think of a circuit. Okay, so right here, big one is positive, small one is negative. A simple circuit will go like this. Okay, forget about everything else, right? I have a positive end and a negative end. So we think of the positive end as having a high potential going to the low potential. So if I had a positive charge, remember when people came up with this, when they thought of this, there was no just such thing as an electron in their mind. They had never even thought of such a thing, so they always thought it was a positive charge. They only found out later that what actually moves are electron and they are negative. So this is comparable to a cliff again. So let us grab this and unravel it into another cliff. However, I'm just going to have this big end and this small end, and it'll look like that. So I grabbed this and unraveled it. So if I have some charge here, it's going to want to start here and go around this loop and end here. Same thing if I have some rock, it's going to want to start from the high potential and go to the low potential. This should be negative. So it's going to want to, so if I have a charge here, something with charge, it's going to want to start the high potential, go to the low. If I have something with mass, it's going to want to start the high potential and go to the low. That's how these are comparable. So, and the difference between the potential is what we call V, voltage.